Alright, so we're looking at Chapter 7 of Finite Mathematics, and the topic is linear programming. And the intent of this is to introduce some matrix terminology. Alright, so first we talk about polyhedral convex sets. You may have some idea of what this means. Certainly you know what a polyhedron is. Some people may know what convex is. You've seen in calculus convex and concave. But in this area, convex has a very specific meaning that we'll talk about later. And of course people know what a set is. All right. So first of all, you have this ordinary equation that you've seen before, and we're going to write it in matrix notation. So this is important to get here, is that this left-hand side can be considered as the product of two matrices. And the two matrices are here, minus 2, 3, and that's one row, two columns, and times x1, x2. This is two rows, one column. Now you might say these are not matrices, but they're vectors. We can still call them matrices. This is a 1 by 2 matrix. This is a 2 by 1 matrix. And the multiplication that you do is matrix multiplication, row times column. So the left-hand side here can be considered as A times X, where A and X are two matrices. The right-hand side is just B. And the point is made down here, the point is made down here that you can identify the solution set of this equation as a set of points in the plane, and he calls that a locus. And here's the locus of points corresponding to minus 2x plus 3, minus 2x1 plus 3x2 equals 6. And the plot set as a line, as well, hopefully you would expect. Then we get on to inequalities. X less than or equal to b, ax less than b, x greater than or equal to b, or x greater than b. So that's going to be on one side or the other of this line. Now I've talked about that in a previous video. If you want to know which side of the line it is, you can test 0, 0, and that will tell you pretty much which side of the line is. So for instance, if I want to know in this inequality if it's below or above the line, I put in 0, 0, that's true. So in that inequality it's below the line. Right, since it's less than, the line itself is not included. So we can skip through this fairly quickly. Terminology, this, if you include the line, that's called the closed half plane. So since we will be doing inequalities with the equal sign, we'll be dealing with closed half planes. Now up here we dealt with a single equation, but we've seen that in linear programming typically you want to deal with several equations or several inequalities. So how do you deal with that in this matrix notation? Well, essentially what you do is you stack the equations one on top of the other, and then you just stack the matrix to make a bigger matrix. So let's see how that works down here. Alright, so here, for instance, we have this matrix A. Now it's no longer a single row, it's 1, 2, 3 rows. Each row represents a different equation. The first equation is minus x1 plus 0x2 equals 0. Second equation, 0x1 minus x2 equals 0. Third equation, 2x1 plus 3x2 equals 60. Now he's using inequalities, so we can say, we can express this as ax less than or equal to b. So let me just write that out explicitly. This first line is minus x1 plus x2, so we'll just write it here. So we have minus x1 less than or equal to 0 minus x2 less than or equal to 0. And then we have 2x1 plus 3x2 less than or equal to 60. Alright, so minus 1 less than or equal to 0, that's the same thing as x1 greater than or equal to 0, x2 greater than or equal to 0. So these are the usual positive variable conditions that we've seen before in linear programming problems. And just like we've seen before, each one of these constraints gives you a half plane. So the first x1 greater than or equal to 0 gives you to the right of the y-axis. x2 greater than or equal to 0 gives you above the x-axis, and then this one gives you below this line. So you get this shaded triangle. So same old stuff, but new terminology, a new way of expressing, and more elegant, more compact. And you'll see that this way of writing things and expressing things aids in developing the theory. The other thing to notice is that we've dealt with two variables so far, but this terminology or this setup can be extended to any number of variables and any number of equations. You just get a larger matrix, and on the right hand side notice that it's not a number anymore, but it's a vector. So you have a larger matrix, larger vector of variables, and a larger vector on the right hand side. But the principle and the compact form of writing it is exactly the same. No matter how many equations, you can still write it as ax less than or equal to b. So if you think for a moment about the general case where we have more than two variables, then what the result of an equation like this, a1x equals b1, or aix equals bi, is a hyperplane. Now, when we had two variables, it was a line. If you know anything about in three variables, if you do this in three variables, if I have a1x1 plus a2x2 plus a3x3 equals b, in three dimensions that's a plane. In higher dimensions, although you can't really graph it, we simply call it a hyperplane. You can see in one or two dimensions it's linear, it's flat, and it's natural to call the extension to higher dimensions a hyperplane. Right, now, on the other hand, if you are taking inequalities of the form ax less than b or ax bigger than b, these are called half spaces. Now here, notice this says aix, so this is just a single row that we're talking about here. We're not talking about multiple rows yet, just a single row, single equation. This would be single inequality. The single inequality produces an open half space. And these, when you have the inequality and the equal sign, that's called a closed half space. So when we are taking several inequalities and we want something to satisfy all of those, you are taking the intersection of half spaces. For us, it's closed half spaces. You're taking the intersection of closed half spaces. And here's where we have the definition of polyhedral convex set. The intersection of a finite number of closed half spaces is a polyhedral convex set. So the triangle that we created here, this is a polyhedral convex set because this to the right of the y-axis is a closed half space, above the x-axis is a closed half space, and below this slant line is also a closed half space. All closed half spaces. Now you might think this is unnecessarily restrictive because we're only looking at less than or equal to inequalities, but it's very easy. If you have an inequality that's greater than or equal to, you just multiply through by a negative sign and you can get an inequality with a less than or equal to. So really we have not lost any generality by considering only inequalities of the form less than or equal to. Alright, so he says here the terminology polyhedral convex set is used because these sets are a special example of convex sets. So in mathematics, a convex set is a set that whenever u and v are points in C, the entire line segment between u and v also belongs to C. Okay, so if pictorially that means something like this. If I have some set here and I take any 2 points in that set, here and here, and I draw the line between them, then the entire line is also in the set. All right. So if I call this A and this B, right, any point on this line here is what you'd call an affine. It's called a convex linear combination of A and B. This point here is going to be some multiple of A, I'll just call it K, and then some multiple of B, but the multiple of B has to be 1 minus K. Notice that these coefficients add up to 1. Okay. So any point on this line can be expressed in this way, where K is between 0 and 1. If K, you can see if K is equal to 1, then we get A. If K is equal to 0, then we get B. And if K is 1/2, you would get the midpoint right in here. So anything else is going to be on that line segment joining A and B. So convex means that the line segment joining any 2 points in the set is still in the set. So an example of a non-convex set would be something like this. I'll just draw it down here. This is non-convex because I can take points A and point B and I can draw the line, and there are points on that line that are not in the set. So I think that's good for our introduction, and that's it.